Okay, so good morning, everybody. Thank you for coming. I'm wishing all of you very, very happy and prosperous and peaceful and safe. Happy New Year. So today is December 31st, 2020. It's the last day of this amazing, fantastic year in the history of the human race. We will never forget 2020. 2020 was very famous because it was very often referred to as the year when the world was going to come to an end, according to some predictions by Mayan civilization and all that. Of course, there is still some time left in this year, so we should not lose hope yet. Maybe the world can still come to an end in the next 18 hours or so. But you know, I have a feeling that we'll make it to 2021. And yeah, so after having experienced everything in this year, I think all of us have become stronger and wiser and smarter. And the thing is that, see, if you look back at history a little bit, you realize that something like what has happened in this year is only a trailer. Okay, this is not the main event. Like for all of us, this pandemic has been such a life-changing event. So we think that nothing worse can happen. So I'm here to give you bad news that this is just a trailer. Right? So if you look back in history, we had the last pandemic was in 1918 or so. Now, after that, for the next 20 years or 25 years after that, until near the end of the Second World War, life just became more and more complicated. And there were events and there were times when things were much worse than anybody could imagine. Right? People did such things which were so horrible. So I mean, if history is any guide, then we should not celebrate prematurely. We should instead prepare for a upcoming future which will be which can be in many ways very dark. So the point is not to scare anybody, right? The point is just to state a simple fact, right? And so yeah, we will all have to grow up very quickly. So because we are entering the age of artificial intelligence and robots, and also of genetic modifications using a tool called CRISPR. I don't know if any of you have heard of CRISPR. CRISPR basically allows almost practically anybody to engineer perform genetic engineering on organisms. And so you can imagine what people can do with such tools. So you have the unlocked potential of genetic engineering, the awesome power of artificial intelligence, and all of that combined with robotics as a new technology. That's absolutely right. So we should hope for the best, but prepare for the worst. These are very wise words. They're coming from Sudeep. I want to mention this because they are very wise persons. Okay, so let's continue talking about much more normal things. So before I talk about this thing, addition of angular momentum, there are a couple of important aspects of these angular momentum operators which I need to mention. So basically that involves this. In polar and in spherical coordinates. Okay, so one thing that we have seen, right, is that so angular momentum is this operator, right, I cross P. And so what we have normally done is we have written P as I h bar times the gradient minus h bar times the gradient. Right? I hope that all of you understand this notation. I'm sure all of you do. You are all coming regularly to this class, and but if you don't, if you have any doubts at any point, you please let me know. Okay. So you get I h bar. The gradient is basically right this operator. So in terms of this, we have written down the angular momentum operator. So for example, Lz becomes minus I h bar x dy minus y dx. Okay. But this is in the Cartesian coordinates, right? So this is in Cartesian coordinates. But there is but if you have a system with some angular momentum, then that system has a certain symmetry, right? What is that symmetry? It's rotation. So it is better to adopt a coordinate system which is more suited to this. So we should look at a coordinate system which exhibits some sort of rotational symmetry, right? So we can, for example, if you are in 2 dimensions, you can work in polar coordinates, right? Or if you are in 3 dimensions, you can work in cylindrical coordinates. So cylindrical coordinates, how many axes of symmetry are there in cylindrical coordinates?
One.
There's just one axis of symmetry, right? Or you can work with spherical coordinates. How many axes of symmetry are there in spherical coordinates? There are three axes, right? So 3 independent axes. So so if you switch to polar coordinates, for example, if you stay in 2 dimensions, just as an example, then what happens is that this angular momentum operator in 2D polar coordinates, that means ignoring the z-axis for the time being, and we can do that, right? Because there is no dependence on any z coordinate here. This becomes minus I h bar rho phi, right? Where what is phi? Phi is this. Phi is a polar angle. Right? So this is x, this is y. So in polar coordinates, we write the coordinates of any point as r phi, right? And there will be a factor of r also. We have to put a factor of r to make things, so to give things the right dimension and dimensionality. No, there's no factor of r. Sorry. Yeah, because this is dimensionless. Okay, so then in 3D, right, if you are in cylindrical coordinates or in spherical coordinates, the expression for Lz remains unchanged. Okay, so for example, if you are in cylindrical coordinates, right? So you have x, y, z, and any point on the cylinder. So you have cylindrical. You imagine that your space is filled with cylinders of varying radii, right? Like that. So each point so for any point, how would we write down the coordinates? We would write it as r, phi, z, right? R phi, because you would have this would be your phi, this would be r, and then this would be z. In spherical coordinates, you have your coordinates have you have x, y, z. You have this angle phi, this polar angle, and then you have this angle theta, which is the angle from the z-axis, azimuthal angle, and the radius. So it's r, theta, phi. And I think you all know what these coordinates are, so I'm not going to like talk too much about that. Right. So if you work in and generally we are only, I mean, for many cases we only look at Lz, right? So for instance, if you have a wave function psi, which psi of r, right, the component of the wave function, remember, and let's say it can be written as some product of something like this, let's say. Right. Let's say it can be written as a product of some functions like this, or some function of r and theta and multiplied by some function of phi. Right. So it's a separable. And then, so you want to ask, what is the effect of this Lz operator acting on psi of r, right? So the Lz operator acting on psi of r will just give you the derivative of the polar component of your state with respect to phi. And so if your state is an eigenstate, right, of angular momentum, then for instance it would have to satisfy an equation of this form, right, is equal to some eigenvalue. So m times psi of r. So this kind of an equation would imply that this function will be of the form e to the plus minus, right, I times m phi, right? So if you take the derivative of this, right, so you get this equation basically, because we only need to look at the phi component. So if you look at the phi component of the state, you will just get this kind of exponential. Okay. So, and then one would have a requirement that your wave function has to be single valued. What that means is that if you go around in the polar axis, you go all the way around by 360 degrees, and when you come back, your state should remain unchanged. Okay. So I got disconnected as usual. Can you guys hear me?
Yes, sir.
Okay. Okay. So connecting from this other one. What the problem? Okay. Okay, it's showing up. Okay, so then you would have some sort of requirement that the wave function should be single valued, right? So this requirement would imply that when you take this exponential plus minus I m times pi plus 2 pi, it would have to equal exponent plus minus I m phi, right? So this is only possible if exponent plus minus I m times 2 pi has to be equal to 1, right? And this implies that m will be an integer. So m is equal to 0, 1, 2. So you get quantization of angular momentum from this requirement of single valuedness of your wave function. So one can similarly ask what is, for instance, the Lx component and the Ly component in these coordinates. So the Lx operator in the same way would be some, I'll just write down the expressions, minus sine phi dou theta cot theta cosine phi dou phi, and Ly is minus I cos cosine phi dou theta minus cot theta sine phi dou phi. Okay, so these you should derive. Okay, so this is let's say homework 7 point whatever, I don't remember the problem number that I don't know, 3, 4 or 45, I don't know, something like that. And similarly, you can do the same thing with L plus and minus. Now you remember what L plus and minus is? Anybody? Going to be Lx plus minus Ly, right? It's this ladder operator. Okay. So this becomes minus IH bar e to the plus minus I phi plus minus dou theta minus cotangent theta dou phi. Right? You can just look at the form of Lx and Ly, and you can see that when you take Ly and multiply by I and add it, you will get sine phi plus I cosine phi. So that's where you will get this e to the I phi with some sine, and same thing here. Right? So again, this also goes in this part. Okay, then we come to the most important operator, which is L square. Now L square is, right, and equivalently you can write L square in terms of L plus minus also. So you should be able to do that. I mean, it's, you just substitute, you just look at L plus and L minus, and well, you solve for Lx and Ly and then substitute in here, and you will get 1/2 into L plus L minus plus L minus L plus. And in terms of coordinates, so this will become, in spherical coordinates, minus h bar, this thing, h square, 1 by sine square theta d phi squared plus 1 by sine theta d by d theta sine theta d by d theta. So this is a very important expression. Okay, so this is something that doesn't, almost in practically every physics class you take, you will encounter this expression, right? And what is this called? This is called this is the angular part of the Laplacian. And what is the Laplacian? If you remember, Laplacian is del square operator, right? So in spherical coordinates, the operator del square. So in Cartesian coordinates, it becomes this. Right? In spherical coordinates, it looks like this. What is it? dr square plus 1 by r square L square, if I'm not mistaken, where this L square is this operator. Well, L square without the h bar. So we'll divide by minus h bar square. Okay. And this angular part of the Laplacian, again, we can ask what are the eigenstates of this. So the eigenstates of this expression and can be written as follows. They are basically what we call spherical harmonics.
Sir, your voice is gone.
I got disconnected again. I'm sorry. Don't know what to tell you. For L square, can you all hear me?
Yes.
Yes.
For the L square operator, you get this kind of expression for the eigenvalues, right? And the form of these wave functions of these states are y, lm, theta, phi. These are what are known as your spherical harmonics. Okay. And if you have this function, this spherical harmonic function, so you can write it this as follows. Right. So we can write, for instance, the state L comma M in this way: y, lm, theta, phi. Right. These are the components of the state. And what would be the basis? The basis would be this theta, phi basis. So you have these eigenstates of theta and phi, basically. One way to think of it is that. And you have an integral. Now this integral would be over the angular coordinates. And you have to remember that there is a sine theta factor, okay, which comes in this spherical coordinate. So this is what this Lm state looks like. So the eigenvalue of L, this is equal to L into L plus 1 Lm, and multiplied by, there's an h bar square factor. And if you take Lz L comma M, you get M times h bar. Okay. So just to remind you, this is what we have. These are the eigenstates of angular momentum. Okay. So we are not doing anything new here. We have worked out all of these eigenstates previously. So group theory, etc., etc. I think it was in the beginning. All right. So if you start out with, if you remember in the beginning, when we looked at the eigenstates of these operators, right, and we worked through this whole algebra, right, we found that without any reference to the form of the operators, we didn't look at this eigenstate kind of solution. We just looked at the algebraic solution, and we found this kind of a structure, right? So in undergraduate quantum mechanics, for example, you would look at these spherical harmonics. That is what would be the way that you would be introduced to this idea of angular momentum. Okay. And these states are orthogonal. So if you have L prime comma M prime Lm, you would get delta L prime delta M prime. And this follows from the orthonormality of these YLM states. So in mathematical physics class, for example, you must have studied that, I'm sure. And so this is equal to YL prime M prime theta phi, YLM theta phi, sine theta d theta. When you take this inner product, what you would do is, again, you would have one copy of Lm with some angle theta and phi. Then you would define another copy of L prime, the bra vector, with theta prime and phi prime. But then the inner product between, when you look at this state, what would happen is you would take the inner product between theta prime and phi prime, this, and and theta phi, right? And this would give you delta theta theta prime, delta phi phi prime. And so when you insert this into the integral over one of the set of coordinates, the primed or the unprimed, doesn't matter which one, will vanish, and you'll be left with this expression. Okay. All right. And okay. Then one can look at the explicit form of these YLMs and all that. I will not go into that, okay? Because then that would take us. I'll leave that for your mathematical physics course. Hopefully that it will be covered in your mathematical physics course. Okay. Now the next thing is that one of the main applications of angular momentum is to look at the hydrogen atom, right? That is one of the most important early successes of the theory of quantum mechanics, right? So Schrodinger, when he first developed his equation, he wrote like 4 papers on this, and in one of those papers he solved this hydrogen atom problem, and he showed that this wave equation gives you the spectrum of hydrogen, right? So what is the spectrum of hydrogen? The spectrum of hydrogen is this set of lines, right? N is equal to 1, 2, 3, 4, right? And then you have these different series. They are known as Balmer series, Lyman series, Palmer something. They're like
Bracket.
3 or 4 Beckett, right? So Bohr had given a model for the atom, right? Bohr had said that that if your energies are quantized in this way, so where E is the energy of the nth eigen of the nth orbital, minus 13.6 eV divided by n square, right? Then you would get you would reproduce exactly this these different spectral series. But in Bohr's model there was no, like, it was a what we call a heuristic model, right? Heuristic meaning that he used physical reasoning to reach his results, but he didn't have like a complete mathematical theory which described how all the parts of the system were behaving. So this is what was accomplished by Schrodinger, right? And so we have the Schrodinger equation, right? And again, what is the Schrodinger equation? P square by 2m, operator P square by 2m, operator V, right, acting on the state psi, is equal to the total energy operator acting on the state psi. And this is the Schrodinger equation. Or yeah, this is the general Schrodinger equation. And you can have a time dependence here. I should mention that. Psi of r comma t, E psi of r t. And when you factor out the time dependence, you are left with the time independent Schrodinger equation. So you will get, when you insert in minus h bar square by 2m del square plus VR, this whole thing acting on psi of r is equal to E times psi of r. So this is the Schrodinger equation. Now, for the hydrogen atom, how do you how do you set up the problem? So for what you have in the hydrogen atom is you have a proton, right? Which is mass of the proton is much greater than the mass of the electron, right? It's about 2,000 times the mass of the electron. And then you have an electron, right? And there is a force between these two. And that force it's an attractive force, right? And it's a radial force. That means it only depends on the distance between the two particles and doesn't depend on the directionality, right? And what is the associated potential energy? The associated potential energy, right, is minus K Q1 Q2 by R, where R is the radial separation between these two. So for instance, if you are in a hydrogen-like atom, that means if you say that you have some atomic number Z, this means number of protons is equal to Z, right? Which is equal to the number of electrons. And ignoring the neutrons, because while the neutrons, they don't play a role in this Coulomb interaction, at least, you know, to the first order of approximation, this becomes minus K times Z square E square by, right? So this is the form of the Coulomb potential. You get this 1 by R. Now, how should you write this Laplacian del square, right? To write the Laplacian, you should use spherical coordinates because your problem has spherical symmetry, right? The way that you can see that the problem has spherical symmetry is because everything is a function of R. There is no dependence on theta phi, right? So if your potential, for instance, depended on theta phi, then you wouldn't have spherical symmetry. This is what we mean by spherical symmetry, right? Something which only depends on the radial coordinate. And because what is the symmetry operation? The symmetry operation is rotation. What does rotation do? Rotation changes the theta phi part of your coordinates. It leaves the r part unchanged, right? So one can write down what this Laplacian is. And yeah, I knew I made a mistake in the earlier expression. It's a little bit more complicated than this. Something like 1 by r square dr, r square dr, like that. And then plus your this L square plus 1 by r square L square. So this is the radial part of your Laplacian. This is the angular part. Okay. So what you would do is you would when you write down the full Schrodinger equation in inserting the expression for the Laplacian, what you get is the following: r square dr, r square dr, plus. Now what happens with the angular part? Now remember that the angular part, when it acts on the state on your spherical harmonics, so you assume, we make the assumption that our wave function psi of r can be written as some product of your spherical harmonics and a radial component, right? So this is the separation of variables method. So what happens when you look at this angular part of the Laplacian, and it acts on this state. It will have no effect on the radial component, right? It will only act on the YLM part. And when it acts on the YLM part, what will it give you? It will give you just this eigenvalue, h bar square LL plus 1, right? So when I insert that into my Schrodinger equation, what happens? I am left with this kind of an expression, 2mr square. So let me write it slightly differently. Plus minus h bar square by 2m. This h bar square is common. H bar square by 2m is common, right? It's just the overall multiplicative factor in the Laplacian minus h bar square by 2m. Right? And then you get the contribution from the L square part acting on YLM. That gives you this eigenvalue L times L plus 1. Right? And then there is also a factor of 1 by r square, which I mentioned to you earlier, divided by r square. This is the result of the kinetic energy part of the Schrodinger equation. Then you have to add the potential also, so you get V of r. Right? Now this whole thing acts on what? It acts on your state psi. But you remember that when you use separation of variables, what happens? You divide out by one of the factors, right? So if you divide out by YLM, you are left with this RR is equal to E times RR. So this is what your Schrodinger equation finally looks like. Then you can solve it and do all kinds of fun things. So I won't discuss those solutions right now. Okay, but I will try to come back to it again, because I really want to talk about this addition of angular momentum. Questions? And I know that at this point I'm not explaining every single aspect, because I assume that those of you at least who come regularly to class and who do the exercises regularly, right, that you have picked up all of these techniques along the way.
Sir?
Yes.
Sir, won't there be a factor of minus h bar square in that term L plus 1 divided by minus h bar square?
In which term?
This second term in the Schrodinger equation, second term.
Right. So there is a factor of minus h bar square. Eh?
No, in the denominator, because when we wrote the Laplacian,
No. So this is minus h bar square. This is minus h bar square. Cancels out, no?
Okay, sir.
Right. Because when I write down that Laplacian, yeah, you're right. Actually, this was my mistake. This should not be there. This minus h bar square should not be there at all. So if you get rid of it, because this is just L square, the operator, minus this h bar square comes when you take the eigenvalue. So my mistake. I apologize. Okay. And it is also important to remember one more thing, which is that one doesn't go directly to this equation. What actually happens is you start from the two-body problem. So let me remind you about this, and maybe I hope you have covered this in classical mechanics. It's one of the very first things that you normally do, right? So the two-body problem means that how would you write down the Schrodinger equation, or if you forget about the Schrodinger equation, how would you write down the energy of two particle state of a two particle system? So what would be the total Hamiltonian for two particles, right? It would be this P2 square by 2m2 plus V R1 R2. This would be the classical Hamiltonian for two particles, right? Because you have an electron and a proton, they have different masses, for instance, right? So starting from this, how do you get to this expression, right? Or starting from this, how do you, so here you have two different momenta, P1, P2, and two different coordinates, R1, R2. So what happens? So what happens is that you actually first you go to the center of mass basis. You go to the center of mass coordinates. So in the center of mass coordinates, what you have is you have these two particles, let's say M1 and M2, right? And the center of mass will lie somewhere over here. And we say that, have you covered this problem in classical mechanics? I don't know. I hope you have. Huh?
Yes, sir.
Right. This is the most straight line नहीं बन रही है. So this is our center of mass, and with respect to this point, you define the locations of these two masses. So this is vector R1 and vector R2, right? And when you work in these coordinates, what happens is that your Hamiltonian becomes the sum of two parts. One becomes the center of mass Hamiltonian, right? So this, what this does is it measures the total center of mass energy of the whole system, right? And then you get another expression which involves the momentum with the reduced mass. So the reduced mass, if I'm not mistaken, is like this. And then in this expression, we use the fact that the potential is purely a function of the difference between these two coordinates. So this becomes purely a function of R, right? So then we go to the center of mass frame of reference. So in the center of mass frame of reference, what is the total kinetic energy of the system? What is H center of mass? It is this quantity, right? So in the center of mass frame, what is the momentum of the system? Anybody?
0.
It's 0, right? So this is just 0. So you are left with this part. And this part, so this just gives you the regular momentum. But now this momentum is defined purely with respect to this center of mass coordinate. And since your proton is 2000 times more massive than the electron. Right? So if you look at the proton and the electron, and you ask where is the center of mass lie, the center of mass lies almost right next to the electron, right next to the proton, right? Because if this is 2000 times greater than this mass, then the center of mass will be closer to the more massive object by the same factor. Right? So if they were the same mass, the center of mass would be in the center. Right? If one was twice as big as the other, the center of mass would be 1/3 of the way from the big mass and 2/3 of the way from the, right? And so on like that. So when this is 2000 times more massive, the center of mass will be 1/2000 times as close to this one, and almost completely, so it would be this separation of the center of mass from the proton is negligible. So in this approximation, you can neglect the motion of the proton. Right? And it's the same thing that is used for solving the gravitational two-body problem also. And what is the reduced mass of the system? The reduced mass, if we look, MP plus ME. Right? Now again, MP is mass of the proton is much greater than the mass of the electron, right? So we can pull out the mass of the proton from the denominator, and we can write the denominator like this. And now this ratio we can set as 0. And so this becomes, the reduced mass becomes the mass of the electron, right? Up to a very small correction, up to order of ME by MP. So in this Schrodinger equation, remember, we write mass of electron, right? Here, this is the thing. But strictly speaking, this is not mass of electron. This is the reduced mass of the system, which is ME times order of this. So when you take the denominator and you Taylor expand the denominator, you would get this. Okay. All right. So I didn't get to addition of angular momentum yet. I'll do that tomorrow. We have one class tomorrow. Right? So when you make these changes, when you
Sir, your voice is gone.
okay, so again disconnected. I have to talk to my network provider. So it is in this approximation that the Schrodinger becomes just a function of R. Okay. Otherwise, if you take into account that the proton and electron, that the proton has a finite mass, then the Schrodinger equation you will have to put some corrections And those corrections will lead to corrections in the energy eigenstates, energies of your states, and your wave functions. But for most purposes, those corrections are not important, right? So I'll leave it here for today, and then tomorrow we'll talk about addition of angular momentum. Okay, and one thing is that I haven't talked in detail about the solution of this Schrodinger equation, because that would take around 2 or 3 classes at least. So if you have the patience for it, we can talk about it. We still have some classes left, but I doubt that anybody would be. I am sure by this time you're all pretty fatigued. Okay. All right. So I've not given you any numerical problems. I mean, but there is this algebra to work through. So please do that. The numerical problems will make sense, will matter only after you have worked through all of this. Okay. Okay. Questions? I hope you know how to derive these expressions. You basically have to look at the expression for, so you look at this LZ, right? And it's in terms of X, Y. So you have to write X and Y in terms of polar coordinates or spherical coordinates, whichever, ones you're working in. And then you have these derivatives, dy and dou x. You have to write these derivatives in terms of r, theta, and phi. So dou r, dou theta, and dou phi. So I hope you know how to do that. Right, you have to use the chain rule. If you don't know how to do that, well, I can explain that to you in then tomorrow's class. Okay, so any questions? Nope. Okay. All right. So I'll see you all tomorrow. Okay.
Okay.
In the new year. So have a safe and happy new year, everybody.
Happy New Year, sir.
Thank you, sir.